All right, day 16. It's another grid problem. We have a start and an end, and we want to find the lowest score we can get to the end. Every turn costs us 1000 points, and moving in the same direction as we're going costs 1 point. So another grid problem, so added, copy pasted from yesterday. CG Math added, we have a vec2, we have a grid. Can create it from a vec chars. Can find and set and get, find all, and print for debugging. So we start by reading all of the lines. And then we create the grid just like we did in yesterday's problem. Iterate over the lines. Map each line to a list of characters. Then we need to find part 1. So we call that this result and we solve grid. And then we can print the result. So how do we solve this? So we absolutely can brute force this by searching like in one direction and then searching turning in the other direction. For me it finishes in about 20 seconds for part 1 and 20 seconds on part 2. But there is more optimal way to do it, and that is to always search the lowest cost first. But we'll start by getting the current position, and that will be where we can find the S character. Then we have a direction, and we start by going east. However, that is 1 in Y direction for me, because X is the column and Y is the X is the row and Y is the column. We then need to keep track of where in the grid we have been and what was the cost of getting there. So we'll create a mutable hash map where the key will be a position and a direction, and the value will be the cost of getting there. Then we will create an open set which holds all of the places we want to explore. So this is very similar to A star, but we want to get, we want to be sure that we get the best path. So we have to search all of the possible. So here we have an open set, so position and direction and the cost that it costs to get to this. So this will be our initial position. So while we have any open, we will search. So here we can panic, because that means we failed the mission. We can now shadow the position and direction. I guess we didn't have to create these variables here. So position, the next one that we are investigating, and we want to remove from the beginning. We could use a vectq, but it doesn't really matter. So the position will be next 0, the direction will be next 1, and the count will be next 2. We then need to check if we have already visited this state, which would be position direction. And then we need to check if we have visited this position. We should only continue if the count is lower than the previous. So if let some prev visit count get key, and key we need to define would be the position and the direction. Then if this is less or equal to what we have this time, we should just continue and search for the next one. If we haven't visited this node before, we should add it into the visited. So the key and the count as the value. So the count is the price that it took to get to this position. Then we need to check if we've hit a wall or are outside the grid. So we can let some character be grid and get on the position. Otherwise we can continue. Then we need to check if we have found the end. Then we should return. If it's a wall, we should continue. So if end, we can return count. Otherwise, if it's a wall, we can continue. Otherwise, we need to search all of the possible directions. So one would be to just keep going in the current direction. So the next position would be position plus direction. The direction is still direction, and the count to that will just increase by 1. Then we should turn 90 degrees. So I'll create a function for that. For deer, maybe yeah, I'll create that. And then we will push that, but then with the cost of 1001, because it costs 1000 to turn and 1 to move. And then we'll do this 3 times. Turn in all directions. So I'll just generate this function, and it's just to flip the x and y, and you just negate 1. And I don't care if I turn right or left. The last thing we need to do is to sort the open set, because we need to have the lowest count in the beginning. So open sort by key the count. Using a priority queue would be slightly faster, but this should not be a problem. And that is the correct value. Now for part 2, we need to do the same thing, but instead when we get to the end, we need to mark that path as one possible path, and then we need to check if there are any other paths. And we also need to check for branches in the path, because if they are of equal count, then we should collect them all. Then we need to store the actual path, so we can mark all of those coordinates in a hash set, so we can count them. So here we need to check if the previous is equal to the count. Then we have to add both of them to the same path. So we can do a just a little to do there. We also when we get to the end, we shouldn't return. Instead, we should collect this as an end. So we can have a list of ends and just push the key and the count. And we only want the ends with the lowest possible count in the end. So we'll create that. And we do not want to return. Instead, we just want to continue searching. Here, we no longer want to panic. But instead, we need to do some things. We need to have a map of where. So when we push into the open, we need to save from where that push was and then store that in a hash map. So, and we can have multiple paths because they can split. So it should be a hash map of a list of keys. And a key is a position and a direction. So we'll call this to from. And we can define what it is. So the key is a position and a direction. And the value needs to be a list of position and direction. We then need to here check where we came from. So in the initial open, we need to add none because this didn't came from anywhere. But here we need to add the key as from. So then we have where we came from. We can just do that so we don't get the annoying lines. So we need to check if we came from somewhere. Then we should set the key to be from. Otherwise, we can just have an empty list. And we need to declare that from is next.3. Now this will only give one path. We need to get all of the paths. So here on the to-do, we also need to check here. But here we no longer want to insert. Instead, we just need to add to that list. So we do to from get mutable key, and we know it exists, and push from. So I think this should work. However, it will return 0. Yes. So now we need to build the path from to from. So we have the ends. So we will find all of the ends with the lowest cost, and then traverse the to from map, and that way build the whole path, and then we will just count how many positions we have visited. And now we want to count positions and not position and direction. So we wanted to count how many seats there are. So we can create a set of those, and in the end we're gonna return the length. Then we can create a stack of that we can flatten the to from to. So now we need to find the ends with the lowest count. So lowest ends, iterate over them. Map, we only want count, and then the min. And then we can loop through all of the ends, and so now we're only interested in the end part. In ends, iterate, and then filter where the count is equal to the lowest. And then we will push this to the stack. And that needs to be unwrapped. Now we can just, while the stack has anything, pop from it, and then use the to from map to populate the seats. So while let some key equal to stack pop, we will insert the position. So we are only interested in the position, not the direction. Then we need to find the to from for the key. If there's not a vector here, it means we are at the beginning. Stack extend v. And this should work. 590. Yes. So yeah, another grid problem. Pretty fun one. You can brute force it. I did when I solved it the first time. But this solution, it runs pretty fast. Yeah. Right.